Hi everybody. In this video, I'm going to give you a brief explanation of a way to think about designing the irrigation system. So I've laid out the sort of design of the garden, and I've put in just a sample orientation of the way you might run pipes to each of the garden beds. And then I've labeled each of the pipe segments with a letter. And I want to start thinking about how are we going to build our spreadsheet. Okay, so first off, we need to figure out how much water the plants are going to need. So part of that is looking at how big each of the garden plots are, looking at what kind of thing might be planted in them, and decisions need to be made about how frequently watering is going to occur and how long of a duration is the water going to be on when watering is happening. But in some way, shape, or form, we're going to develop flow rates that we will assign to each of these garden beds. So for example, if you calculate how much water in total that a garden bed is going to need over the course of a week, and you decide you're going to water once a week for an hour, you can take that entire amount of water and divide it by an hour, and then you know that what the flow rate is going to be, right? A volume per time. So you assign a flow rate to each garden bed for each irrigation event. And now we can look at, let's say we're looking at this garden bed that is over here. Let's see, where's my laser pointer? I think it's this. All right, Q8. Okay, so we've got this garden bed here, and it needs a flow of Q8. So what is the flow rate in pipe J? Well, the flow rate in pipe J is just going to be Q8. So I'm going to write that right next to it, Q8. This pipeline that goes to Q8 runs through this bed to the right of it, and the flow rate needed for that bed is Q9. So coming out of this sort of outlet right here is Q9. And thus if we go back up into, and over here on, I should say in this garden bed over here, we have Q10. So if we look at this pipe segment I, we can say, well, what is the flow rate through pipe segment I? Well, that would be Q8 plus Q9 plus Q10. All of the flow has to go through pipe I that's going to all three of those beds. Likewise, if we look at pipe H up here, we see it's got Q7. G then would be Q7 plus Q8 plus Q9 plus Q10. And then when we get to F, it's going to be Q6 plus Q7 plus Q8 plus Q9 plus Q10, etc., until we get back to pipe segment A, in which we're going to have Q1 plus everything through Q10. Okay, so now if I develop a spreadsheet where I list each pipe, okay, so I'm going to say pipe, and I want to look at pipe A, B, C, D, etc. What information do I need for each pipe? Well, I need to have its length, its diameter. I'm going to put in its flow rate. We just developed up here what the flow rates in each of those pipe segments is going to be. From Q and D, we can include a column for A if we want, and then velocity. Let's do Reynolds number. Let's do then friction factor. And now we also have to consider minor losses, perhaps. And so the way I like to think of it is we have to decide whether we're going to consider minor losses or not, but we have to decide intelligently. So at some point we need to calculate what some minor losses might be, compare them to the major losses and say, are they going to be significant or not? If we're going to include them in our analysis, we might have minor loss coefficients that occur along that pipeline. And then finally we'll calculate, for example, the major losses and the minor losses that occur on each line. When I'm looking at head loss, if I want to say, hey, what's the head loss in pipe A, for example, once I have L, D, F, V, I can use Darcy-Weisbach equation, FL over D, V squared over 2G to calculate H sub L. If I then add my minor losses in, I could have another one that says, what's the total head loss within that pipe segment? Then I could have another table below this where I look at each garden bed, and let's say I number the garden beds 1 through 10 in the same way that the flow, the Q1 through Q10 are numbered. So if we say then garden bed 1, 2, 3, 4, etc., we can say, well, what are all the losses as we go to bed 1? Well, the losses are just all the head losses in pipe A, right? But when I go to bed 2, it's going to be the head losses that are in A plus the head losses in B. And if I go all the way to bed 8, I'm accumulating all the head losses as I go. So I get HLA plus HLB plus HLC plus HLG plus HLE plus HLF plus HLG plus HLI plus HLJ all the way to bed 8. And so what I want to do is I want to ensure that the head I have available at my source, I've got my source over here, the beginning of the pipeline, that the head I have available there is enough to overcome all of these head losses that I just calculated. If bed 8 is the most distant and therefore the highest head loss bed that I'm delivering to, do I have enough head to deliver that much water? Okay, so one key thing to think about here is that this is not a simulation. We're not developing a model that is going to simulate reality. We're developing a design tool in order to size these pipes. So not only size, but also develop what orientation or what the schematic of the pipeline layout is going to be. Okay, that doesn't mean that when we turn on the water, that these exact flow rates are what is going to come out of each outlet. Part of what I mean by that is if we think about what's actually happening here, we've talked a little bit about parallel pipes before, right? So we have a pipe and we have two branches that go to the same point and then continue on. And we've said that the head loss in, say, this segment right here is equal to the head loss in this segment right here. The flow rates in each branch are not necessarily the same, but the total flow rate entering each junction is equal to the total flow rate leaving each junction. What's happening in an irrigation system like this is that we're delivering water essentially in parallel to a bunch of points that are at the same head. And what is that head? Well, it's atmospheric pressure. So a way of thinking about it is it's like a parallel pipe system, but we are delivering always to the same head or the same pressure, but it's atmospheric pressure. So the head loss through each branch here has to be the same, right? We have one value of head here and one value of head here that's the same as the value of head here. And so the flow is going to split in order to make sure that the head loss in the top branch is equal to the head loss in the bottom branch. What does that mean? Well, if I look at the schematic up here, technically the flow is going to distribute itself so that the head loss along this pipeline to Q1 is the same as the head loss all the way around to Q8. And so most of the flow would go to Q1, because there has to be a lot less flow here so that the velocities are low, so that the friction losses are also low. Because there's so much more length here that's accumulating for the Darcy-Weisbach equation than there is along this path, right? So you have a lot more flow going to Q1 than to Q8. What do you do in reality to combat that? Lots of things. You can change the design of the way the pipelines run, right? I drew one example here, but there are other ways that you could lay it out so that each branch, for example, has maybe more of a equal or close to equal length associated with it. You could add valves in the system, so you could add control. You could throttle flow down at certain points. You could have different. You could have multiple different watering stations, essentially, so that not all the beds are on the same line. You could water them at separate times, for example. You could. What else could you do? Well, there's different kinds of actual outlets. There's sprayers or nozzles or drippers or other things that could control flow at the end of each line as well. And so what I think we're looking for here is we want you to develop this design tool where you can prove to yourself that the head you have available, however you're developing your water source, is enough to overcome the anticipated head losses in each of the branches, and to go through some amount of design to try to balance out the head losses, or at least build in a way that you could control the flow to these different outlets in some way that they could be approximately or close to what you want them to be, i.e. not all of the flow going to bed 1 with very little going to bed 8. How would you design this so that it's more similar? Now, you're not going to purposefully, for example, some people have done this in the past, like, hey, Q1 needs more head loss, so instead of this being like a direct connection here, hey, let's make this pipeline go like this, for example, so we get more head loss through there. Not a good idea. Adds cost, adds complexity, it's silly, right? And a better way of doing that is just adding a valve to that outlet so you could throttle it down if you wanted to. Now, there's lots of different options here. I'm not trying to be exhaustive in the way to approach this, but I just want to give you an idea of where you could start, and then feel free to modify your spreadsheet in some way as necessary to match what your design is. Okay, so hopefully that's helpful. Good luck.